Okay, so let's finish up our towers of Hanoi here. So currently inside of play, we're asking for the source and for the destination. We'll go ahead and do this in two separate pieces. So we're going to go ahead and pop something off. So we're going to say disk the move is equal to this dot the towers at source pop. So we'll hold on to that. That way we have the ability to push it back on if we needed to in a few minutes. All right. So we have the move. Then what we're going to push rather is the move. Now we need to go into our push function and have our push notify us if it was successful or not. All right, so we'll go into tower. We know pop. Well, generally speaking, we know pop will be successful. At the very least, it'll return a null if there's a problem. But push doesn't return anything for us. So what we're going to go ahead and do is we can have push return for us a error code. We can do it several different ways. We could do it inside of a try catch. In fact, actually, let's do that. Let's do that. We're going to leave it as a void. And instead of just printing out an error, we're going to say that this guy throws an exception. So this is how you build in an error. Otherwise, you could have had to just return an int, maybe a -1 if it didn't work, or a 0 if it did. That probably would have been the easy way of doing it, but I'll just show you how to deal with exceptions. So we're going to say this guy throws an exception. I'm going to steal this string here. And we will throw a new exception, illegal move. All right, so rather than just printing out an error message, this will actually raise an exception, letting whoever called this know that something bad happened. Okay, and we're just raising a generic exception in this case. So now our push either just works or screams. That makes sense? Screams as in I have an error, screams. Now that we've written push to work like that, this method here must be inside of a try catch. So we're going to surround it with a try catch. So we are going to try to execute this line. If there was a problem, what are we going to do? Well, we can actually leave the stack trace in there. But so that'll just display our error that there was that it was an illegal move. But what we will do is we'll say this dot the towers at bucket source dot push the move. Okay. Similarly, this guy needs to be put in a try catch. Okay, because he can also throw an error. We happen to know that this won't be a problem, because we know we're pushing it right back where we just popped it from. That's a legal move. Okay, but we still need to go through the motions, put this guy inside of a try catch. And I'm just not going to do anything as a result of the try catch. So we'll try to do this. We know it'll always work. and we'll go through the motion of catching an exception. We'll have to call that E2 or something because we already had an exception E up here. All right, so to play, we're going to prompt them for a source tower, read it in, prompt them for a destination tower, read it in, pop the element off of our source tower. Now, after this, we really only want to do anything if the move is equal to null, meaning whatever we just popped was nothing. We just popped nothing, that means we have nothing to push. Correct? So we can do continue. Continue says, go to the end of this loop and loop back up. Make sense? Skip this iteration. So if the move is null, just continue, which will prompt them another source, another destination, so on and so forth. We don't have to worry about pushing anything back on because what we popped was nothing. All right, so we'll pop from our source. If it was nothing, we're going to ask them to do this all again. So we'll continue, which will zip back up to the beginning of the while loop. Otherwise, if we're still kicking right here, we're going to try to push the move onto the destination tower. If for some reason it didn't work, we'll go ahead and push the move back onto the source tower, undoing our move, if you will. Num moves only goes up under what condition? Yep, so only goes up here. So we're going to push it, and num moves will go up by 1. If something bad happens in here, this won't occur. Okay? So now, if we run this, no, our push throws an exception. So we need to do this as a try. And we know we're going to be okay there. So a little inconvenient, but better safe than sorry. This is probably the object-oriented way of handling errors with exceptions. Huh?
You should use a runtime exception.
Why?
Because it's unchecked.
You mean here?
No, in the throws method.
Yep.
You should use runtime exception. So every place that you know that this place will never throw an exception.
Correct. So you want to do it as a runtime exception. That way you don't have to deal with it at this level. Mm-hmm. But dealing with it at this level makes us become aware that this push method, like I said, I like being explicit. Okay. It makes us be aware that this push method has something special about it. So I get what you're saying. When you surround this in a try catch, this tells us that there's more to meets the eye to push. Because what you want to do is with a runtime exception, you're going to choose to surround it in a try catch in here, knowing that this is when something bad can happen. And then you're just going to choose not to do anything with it here, which is fine. Yours is probably, from a coding perspective, cleaner. I just like the idea that this reminds us that there's something fishy inside of push. All right. So source will say 0. Destination will say 1. Source will say 0. Destination will say 1. This is going to give us our stack trace saying it was an illegal move. We're still kicking. Let's see. We're going to go from 0 to 2. There's that. Now we're going to go from 1 to 2. Then we'll go from 1 to 2 again. Nothing to pop. So another exception, but we're still kicking. 0 to 1. 2 to 1. 2 to 0. 1 to 0. 1 to 2. 0 to 1. 0 to 2. 1 to 2. Okay? Now, we need to know now that we're done. Okay? Because remember, we're currently inside of an infinite loop here. Inside of Towers of Hanoi. We're just going to keep doing this forever. Until something breaks us out. So, how do we know that we won?
When all the discs are in tower 2.
The length is 3 of the tower.
Num disks. Num disks of it is 3. Not that we can't do the length of the array, because the length of the array will always be 3. Is the way we've written it, right? Okay, so, but num disks, if num disks is equal to 3, we know we're done. So after we've made a move, we'll ask the question, if this dot, the towers at bucket, let's just get through this. The towers at bucket 2 dot get num disks. If that's equal to 3, we have a winner.
But you gotta display your number of moves first too.
Well, when we have a winner. So if we're in here, we have a winner. So we'll say system dot out dot println winner completed in num moves, number of, well, I'll just say num moves moves. Something like that. And then finally, break, which will get us out of this infinite loop, out of the while loop. So 0 to 1, 0 to 2, 1 to 2, 0 to 1. It's 2 to 1, right? 2 to 1, 2 to 0, 1 to 0, 1 to 2, 0 to 1, 0 to 2, 1 to 2. Winner completed in 11 moves.
One less than on your web version of it. Said that's one less than your web version of it.
Can't be.
Yeah. You did that one in 12 moves.
I think 11 is the minimum number. Oh, it is 7. So doing in the minimum number, I would do this, 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 this. Yeah. It's easier to see on here than our crappy display.
Very true.
All right, so does that fulfill the assignment? Does that do everything the assignment was supposed to do?
Yeah.
All right. So let's just let that die a slow death. If I were to go back and rewrite the display method, which I don't want to do because I want to make sure I give you enough stuff for your homework assignment, the way I would implement it is I would create especially if we're assuming, which we did in this case, 3 towers, and even a height of 3, I would create a 2-dimensional array, a grid. So rather than doing all this padding stuff and things like that, I would just mark where the center of the 3 towers were and say, display all those disks along this column inside this grid. Display all these disks inside this column. Display all these disks inside of this column. So then we wouldn't have to worry about spacing being off when we move disks from one column to another, and it would just be cleaner. The limitation of that then becomes that as our game board gets bigger, if we decide to have more towers or more disks, we need to expand that map, expand that grid. Not the end of the world. Realistically speaking, if we were, going to take this to the, Towers of Hanoi professional level, we probably would want to have a graphical user interface for this guy. So we'll call this good enough, I guess. All right, so now I want to talk about a tree data structure. Striation, tree data structure. So tree data structures come in several different forms. So we have something called a binary tree. Oh, he's gone. He's zipping around. Okay, so we have something called a binary tree. A binary tree has a root node with exactly 2 child nodes. Or we could say with at most 2 child nodes. All right, so that would be a binary tree. If we're showing a picture of that,
Oh, so each row is a node?
so that might be a binary tree. Every blue box is a node. So here's the head of our list. All right, but it's the head of the tree, the root node of the tree. This root node has 2 child nodes. It has this guy and it has this guy. All right, this node, which is also the root of its own tree. Okay, so a tree is a collection of trees, linked list of trees, if you will. So this node has 1 child, this guy. This node has 2 children, this guy. This node has 1 child, this guy. So in a binary tree, each node has at most 2 child nodes. This guy has no children. When a node has no children, it's known as a leaf node. Okay? Nodes with 0 children are known as leaf nodes. All right, so that's a binary tree from a picture perspective. That's what it looks like. We then have something called an n-ary tree. Okay, very similar to a binary tree in that it's a root node with an arbitrary number of child nodes. Still, nodes with 0 children are still known as leaf nodes. But every node can have an arbitrary number of children. You're not limited to 2. Okay? Now, there's other trees that we'll talk about later. But for today, we're just going to start exploring trees. But this being our first definition of binary trees, actually, next time we'll talk about binary trees in terms of them being ordered binary trees. So typically the nature of a binary tree is that the nodes are self-sorting. Okay? So, more trivia knowledge. An n-ary tree does not require this. So we're actually going to be focusing on n-ary trees today and for the homework assignment. So n-ary trees essentially store data in actually let's make sure we give ourselves a more than 2-child situation. So here's an example where a node has 3 children. Okay, so this would be an example of an n-ary tree. Okay, each of these has some sort of data in it. These are nodes just like our nodes of our linked list. When we think about linked lists, we're thinking about them as storing an arbitrary collection of data, right? You know, arbitrary being it can be of any length. That was the advantage of linked lists. We didn't have to know how big the data was before we started storing it. Now, stacks was just an abstraction of linked lists that allow us to work with a linked list in a very specific way, pushes and pops. Queues is an abstraction of linked lists that allow us to work with linked lists as if it's a line. NQ, DQ, get at the end of the line, come out of the front of the line. Thing that got at McDonald's. Okay? Now, all those are singly linked structures. Singly linked structures. We'll look at some doubly linked structures where they can go backwards through those as well. It's more of an efficiency thing, doesn't really change the problem solving with it. But when we look at a tree, these solve a different type of problem. When we look at binary trees specifically, they actually solve a sorting problem. You brought up sorting earlier. The reality is what you might do if you wanted to sort a stack, you might pop everything off the stack and put it onto a binary tree, and it would instantly sort. Because binary trees load themselves in a sorted nature. So, and we'll look at that probably next class. But in any case, that's what that data structure is all about. But from a tree data structure like this, which is actually, this is kind of a neat logo I built here. Isn't it? Yeah, it could have been a lot less random, or a lot more random. Trees can solve all sorts of different problems, but a lot of times the problems are arbitrary in nature. So an n-ary tree doesn't necessarily solve a specific problem other than dictate space. So what we're going to do with an n-ary tree in this example is we're actually going to build a little virtual world. Each of these nodes is a room. Okay? Each of these nodes is a room. And every room has exits. So for instance, if we think about this as our little sample here, this is the cave entrance. Okay, this is the entrance to our cave. In this guy, we have 2 exits. Exit 0, exit 1. If we take exit 0, now we're in this room. This room has 1 exit. Exit 0. We take that exit, we're in this room. This room has 2 exits. Exit 0, exit 1. So on and so forth. Okay, so we can actually traverse through this data structure as if it's a mapping of rooms. Make sense? Now what we're going to do is we're going to have each room have exits, which we just talked about, and also a room can potentially have treasure. Treasure, because when you're going through a cave, you're looking for treasure, right? Okay, so we need to go and define some of our data types for this. So we're going to say that a room has a collection of exits and may or may not have a treasure. All right, so keeping it simple, that's the definition of a room. Now, what's an exit? If I'm in this room right here, I have 2 exits. This guy and this guy.
It's a
What's an exit? It's
Child
another room.
Child nodes, yeah.
Exit's another room, right? Okay. When we talk about graphs, then we need to deal with the connection between nodes. They're called edges because graphs can actually loop back on themselves, right? So it works a little bit differently. But for this, if I'm in this room, if I'm standing in that room, I have two exits. I can exit into this room or I can exit into this room. Go ahead.
What do you mean by loop back on itself?
Like if you're in this room, you can get back to this room.
Oh, okay.
You know, so now you need to deal with that edge. You know, think of it like a portal.
Gotcha.
It's going to take you from here all the way back up here.
Like that.
We won't be doing this with graphs. Graphs is going to be a different problem we're going to be looking at. Graphs is a far harder problem we look at. Graphs we look at traveling salesman problem, which if you think about a map of like Wisconsin, let's say you're a salesman and you have to go to 15 different towns on your daily basis. You figure out which order, if your home base is Mequon, what order do you visit the towns that you drive the least distance, but still hit all the towns? So, you know, because you can go from Mequon, you can go to Grafton to Cedarburg, or you can go to Cedarburg to Grafton and back to Mequon. So it loops back on itself, that kind of stuff. So it actually is an interesting time complexity problem. So we'll look at graphs in that light. All right, so that one might be, but might not be. Really depends on where we leave off. Okay, so room is a collection of exits, and it may or may not have a treasure. What do I mean by a collection of exits? I mean it's a collection of rooms, right? And we'll put exits in parentheses there to remind us what those are. But what is a collection? How many rooms how many exits does a room have? N, an arbitrary number of exits. How do we store an arbitrary number of things? Like in a linked list? Just so happens we know how to use those, right? Now I'm going to show you the built-in linked list in Java. So we don't have to write a brand new linked list for this. Okay? And I'm going to show you something called generics. Really cool feature.
Oh yeah, you're supposed to show something about generics.
So here, let's just show it as an example here. Let me kill off all this. Let's just create a new project. All right, and I'll go ahead and just put my quick little hello world program thing together. I did promise you a quiz on hello world, but because I missed last week, I won't give it to you today, but you will very likely get it next time.
Okay.
And we're also running short on time because we took a little bit longer than expected on the other thing. What was I talking about? Oh,
Hello.
gonna build our driver. So as a reminder, you're going to have this exact quiz next week. Make sure you don't forget the exclamation point. All right, so class, public static void main. String array args, you can name args whatever you want. System.println, hello world. Run it, and we know we now have a working program. All right, so next week, right at the beginning of class, you'll have a quiz. Somebody remind me I'm supposed to give you a quiz, otherwise I'll just give everybody zeros. So you either remind me and have a chance. You remind me and have a chance at earning points. Or this is instant zeros.
Oh wait, why do we gotta get the zero because you forgot?
I just told you.
Throw up my hands.
I told you, it's an evening class. I get very grumpy. I get tired.
More so me because I actually work.
Yeah, I don't work. That's true.
I wouldn't say
I spent half my day on the golf course today. Might have tweaked my back, too. I played really well today, but I was on the 5th hole. I don't know, something zigged when it should have zagged. And I thought I hurt myself, but then it just kind of didn't turn into anything. I just kept going. So I guess we'll find out tomorrow.
Please don't end up back in the ER.
Oh, no. It won't be that. I might just have a slight limp, I think. I might have just, yanked a little muscle. I don't think this is going to put me in crutches or anything. I would know by now. All right, so in any case, let's look at the built-in linked list class for Java. So I'm going to go ahead and create a linked list. Notice that I'm in a fresh project here where we have not created our own linked list class. All right, so we're going to create a linked list called LL, and this guy's going to be a new linked list. All right, so that's going to initially create for us an empty linked list. It's giving us the little highlight because it wants us to import java.util. So we'll do that. So now it's happy again. All right. So now what we'll go ahead and do is we're going to say, look at the add method. So add method appends the specified element to the end of this list. All right. So this is like add end. But notice that by default, this guy takes in an object. All right. Add first takes in an object. So, for example, if I say ll.add hello. Hello is a string. Strings are objects, correct? Nothing wrong with that. Then I can say ll.add world. Okay, also an object. Now, if I say ll.get, this allows me to get something at a specific index, or I can get first. So let's go get first. Notice that get first returns an object. This is a generic object. I put a string in, but got a generic object out. Reality is because its strings are so close to the language, this actually would work just fine. But let's pretend like this is a problem. At the very least, it logically acts like it is a problem. Okay, I put a string in, and what I got out was a masked character, right? A stranger. So what I would have to do is if I wanted to print this out, okay, and we're just going to assume this wouldn't work. In fact, here, we'll make it so that it doesn't work. Instead of adding strings, I'm going to add random objects. And I'll add another random object. We're going to be using this today anyway, so I'll introduce random to you right now as well. Okay, so that's in java.util. Just a real quick introduction to random. Random r is equal to new random. This is the way to generate random numbers. So I'll print out 10 random integers. And it's going to be in the range of all integers. That's -2 billion to +2 billion. So good way of getting random numbers. There's another version of nextint that takes in a parameter. Now this will get us a number between 0 and 10. I think the 10 is non-inclusive, so 0 to 9. Okay, so easy way to get random values. Most important thing for us here is if I just print out R, I get a memory address, as opposed to a nice, pretty print string.
But it's the same memory address.
Hmm?
Why is it the same memory address?
Because R, I only created once.
Oh, okay.
Yeah, so it will be the same. I looped through and just print out the value of R 10 times. That's all I did. Yeah, I didn't do anything. I didn't do anything special. So R is a memory address. If I want to get an actual visual value out of R, I got to call one of its methods like nextInt. All right, it has methods you can get next Boolean and stuff like that as well. All right, so that's how I can get actual output out of that guy. So we went ahead and we loaded our linked list up with a couple of random objects. Now what I'm going to do is I'm going to say system.out.println ll.getFirst.nextInt10. Okay, now we know that what we stuck into that linked list was a random object. But when we pulled it out, ll.getFirst, it came out as a generic object. And generic objects do not have a nextInt method. So what do we need to do? We would need to typecast this guy to a random. So now this guy is a random. We knew it was a random when we put it in there. So we knew what we got out was also random. It was just in disguise. Because the people who wrote the linked list class had to write it generically. All right? So it's inconvenient for us. We know what we pulled out of here is a random, but in order to use it as a random, we had to typecast it back to random. Remind Java what that guy actually is. Make sense? So that's a little bit ugly, right? So we have something built in the language called generics, where I can create a linked list of random. And this is a new linked list of random. And now it just works. Why? Notice when I say ll.add, what does it expect? A random object, not an object. Specifically a random object, because I said you are built for holding randoms. Similarly, when I call ll.getFirst, this guy returns a random. So it casts it for me. Make sense? So that's the concept of generics. It's nothing special beyond convenience. You know, it makes it cleaner so we don't have to do all the typecasting with parentheses and stuff like that. Not the end of the world, but cool little add-on. Something you did not have. I heard you said you had your classes in C++ or C? C? Okay, so you never had C++? All right, so it just avoided objects altogether, so it didn't even matter. But C++ doesn't support generics. So you would have had to do the, well, with standard template library, it sort of does. But original C++, it required a third-party thing. Doesn't support generics. C# does. So C# and Java are very similar. All right, but in any case, generics are very handy for us. All right, so that's the built-in linked list class, so we don't have to write a linked list every single time we want to use a linked list. We can just create our linked list, because now we understand linked lists, and we know we know how they work under the hood. So now we've earned the right to use the built-in linked list class. Okay? Now, we want to go and create our room object. So here's a room. And we decided a room is going to be a collection of rooms, that'll be a linked list of rooms, as well as it may or may not have a treasure. Okay, good enough. So we're going to have a private linked list of room objects. We'll call this guy the rooms. And we'll have a private Boolean has treasure. Again, it wants us to import java.util for our linked list. We'll write our constructor for room. We might add something to our constructor shortly, but for right now, we'll just have it be the empty constructor. And this guy will set the rooms equal to a new linked list of room objects. This is kind of the beauty of linked lists, in that we didn't have to define how many rooms this guy's going to have. We'll figure it out later. Linked lists allow us to have an arbitrary number of things. All right. And then has treasure. We'll probably want to do this based on a random object. So why don't we go ahead and say random r is equal to new random. And then say this dot has treasure. I got to import java.util here. This dot has treasure is equal to r dot next boolean. So that'll give us a random true or false. All right. So whether or not we have a treasure or not for this particular room. So when a room is born, we'll go ahead and create the storage container for all of its exits. We didn't actually create any exits, but we got the storage container for its exits. And then we also determine whether or not it has a treasure.
Question.
Yep.
So it's going to generically place a treasure in there, or do we have to set each room?
Well, right now I just have a variable called has treasure that tells us true or false whether there's a treasure.
So totally did not answer my question.
Did you even ask a question?
Yes.
All right, try again.
All right. So when the rooms are set up, do we tell it, okay, yes, you have a treasure, no, you don't, or is the system going to assign it a treasure?
Well, we're having the system assign it right here. This is the assignment of whether or not it has treasure.
Okay.
We created the ability for randomness, and then set has treasure equal to either true or false, whatever random generates for us.
Oh, okay. Gotcha.
All right, so now just quickly, I'll put in a little display method. And in this display method, we're probably going to end up displaying our exits, but right now we don't have any exits. But at the very least, let's display our treasure. So we'll do system.out.println obvious exits. And we're going to have none, because we don't have any exits right now. And then we'll say system.out.println why don't we say, well, here, just to mark it, we'll say treasure, this dot has treasure. All right, so for right now, this is what a room is. It's an empty collection of other rooms, so we went ahead and initialized the linked list, but we never put any exits in there. And then we just determined randomly whether this guy has a treasure or not. Okay? And then a room also knows how to display itself, where we'll just print the line obvious exits. We'll fill that in later. And then we also say whether or not it had a treasure. That's what our room data type is like right now. So inside a driver, I'm going to go ahead and we'll just do a quick little for loop. This is fine. So I'll say room r for int I is equal to 0, I is less than 10, I plus plus, r is equal to a new room. So when we build our new room, this will call the constructor. The constructor will figure out whether there's a treasure in there or not. Okay? And then we'll just tell that room to display itself. Just kind of testing our room constructor right now. So first room had no treasure, then we did have one. So we see it kind of alternating-ish. Some rooms have treasure, some don't. All right, now in our world, we also want there to be, we want our caves to kind of grow. So we can always have some sort of language that allows us to generate a cave. So for instance, we can maybe have some sort of data representation, JSON or something like that, that says, create for me a cave that looks like this. But for our example today, what we want to do is we want a cave to randomly generate itself. So we're going to say that every single room is going to have between 0 and 3 exits. Fair enough? 0 and 3 exits. Actually, let's say 0 and 2 exits, just so we don't possibly run out of memory if we get lucky. So after we figure out how many treasures we have, we're going to say int num exits is equal to r.nextInt 3. So that'll generate a number for us, 0, 1, or 2, right? 0 through 3, not including 3. So now I know how many exits I need to create. And remember, exits are rooms. So I'm going to have a little for loop for int I is equal to 0, I is less than num exits, I plus plus. And what we'll do is we'll say the rooms dot add new room. And that'll go ahead and add those rooms for us. So this tells me how many rooms I need to add. And now I'm going to go ahead and add them to my linked list. And each time we call the room constructor, it's going to come back to this guy for a brand new room, figure out whether he has a treasure or not, and figure out what exits he has. So it's going to kind of grow this grid of caves. So there's a recursive nature to what we're doing here, but it's not actually recursion. When we call this room constructor, we're not calling itself. We're generating a brand new object. Okay? But it is, it looks like it's recursion. So what ends up happening here is we build our very first room. This guy gets a treasure or doesn't get a treasure. And then in this particular case, he randomly rolls the dice and decides he has 2 exits. So he builds this exit, then he builds this exit. But when this exit's being built, he determines whether or not he has treasure, and then he rolls the dice and decides he gets 1 exit. So he builds that. Well, this guy, so everything's been put on hold. It's put on hold now. So this guy now determines whether he has treasure, and he rolls the dice, decides he has 2 exits. So he builds this one. And this guy decides whether or not he gets a treasure or not, and finally we hit the end of the road. He rolled a 0, no exits. Now we're over here, we're able to make the second room for this guy. This guy has 1 exit. This guy has 3 exits, which isn't possible in our current code. So this would be a bug. But this guy has 2 exits. Huh? We said maximum was 3, so this is 0, 1, or 2. So we can't actually have 3 exits. Yeah, by using the nextInt method like this, this will be a 0, 1, or a 2.
Yeah, it means 3 rooms.
2 max.
Because if you
Why?
don't have
0, 1, 0, 1, and
Well, this is going to return an int. So r.nextInt 3 will return an integer. It'll either return a 0, a 1, or a 2.
yeah, that's good.
Yeah.
No, not
But you
0,
can't.
0 rooms.
Yeah, there's three different values that can come back, but if we get 0, we're not creating any rooms. Right? Yeah. 3 different values, but if we get 0, we're not creating rooms. All right, so yeah, so this guy would have been an illegal cave. And there's nothing wrong with doing that. I just know from past experience with the current settings in Eclipse that if you roll the dice good enough and you get enough three exit rooms, you actually run out of memory. Because remember, each of these individual rooms is going to be rolling they're going to be gambling on how many exits they have. So, and when we actually run this, by the time we're done tonight, you'll see as we run it, you'll have some caves that have 1 or 2 exits because we just kind of fizzled out. And you have others that have like 300 rooms in them just because it just kind of grew. So I don't know, it's kind of an interesting thing.
That is pretty cool.
All right, so we'll figure out how many exits we're going to have, and then we'll go ahead and,
So when is this
Build
gonna
them.
break?
huh?
When is this gonna like stop?
As soon as it gets a number of exits to 0,
Good luck.
if we're lucky,
Oh, okay.
for each branch. So keep in mind, when we're here, this guy's going to start off by creating this first room. We know we're going to create a second room because this guy's num rooms is 2. Okay, we roll the dice, we decide we're going to have 2 exits.
Right.
But before we even try to build this exit, we go through the loop and we build this room. This room then rolls the dice this guy doesn't even exist yet. This guy rolls the dice, decides he's going to have 1 exit. This guy rolls the dice, decides he's going to have 2 exits. This guy rolls the dice, and that's where this branch ends, because he got a 0. Then we can create this one, who rolls the dice, he gets 1 exit. Then we create this one, who rolls the dice, he gets 2 exits. This guy rolls the dice, gets 0, branch ends. This guy rolls the dice, gets 0, branch ends. Pop back up here, this guy rolls the dice, gets 1. This guy rolls the dice, gets 0, branch ends, now we're done.
Okay.
But you gotta get lucky. You
Yeah.
gotta finally hit the end of the road.
Oh, that's the rest of our 45 minutes.
All right? No, it builds them real quick. You'll see.
But we
That's why we're using such a. If we did 300,
we'll be here for a
we'd be here for a while. Actually, we probably wouldn't. It would just die really quick. All right. So now that we have actual rooms being generated, when we print out obvious exits, we want to go through and we want to print out the rooms. And we'll index them 0, 1, 2, 3, something like that. Okay? So obvious exits, we're going to do this as a print, so it'll all be on one line. We're going to say for int I is equal to 0, I is less than this dot the rooms dot size. So size is the method that tells us the length of the length of the linked list. Yeah. So in this case, the number of exits. Yep. But it's the length of the linked list. So then I plus plus. So each time through, we're going to do a system.out.print I concatenated with, we'll throw a tab in there to look reasonable enough for us. Okay, so that'll be our obvious exits. Then we'll go ahead and kick it down a line. And then we'll say whether or not it has treasure. Okay, so this is a room displaying itself. And actually, if we want to make it look extra fancy, now you remember this stuff when you do your homework tonight. The paper deals with a older technology that's along these lines called MUDs, multi-user dungeons, which later turned into video games of the type called MMOs, massively multiplayer online. Typically they're role-playing games, but whatever. So you look into those, but specifically the history of these text-based cave crawlers like this is something called a MUD. Just kind of a old geeky history thing that connects your programming assignment to the paper that you're going to be doing. Okay, so there's our display method. So again, right now we're just going to go ahead and we're going to create 10 rooms. Actually, we probably don't want to create 10 rooms. 10 rooms is going to become problematic.
Yeah.
So we're just going to create 1 room. Yeah. So we'll create 1 room, which is going to do this whole branch thing. Okay? and then we'll tell that room to display itself. So there's our, oh, we did get one exit. Did get one exit. So obvious exits, 0 to the north, to the south, or to the west. Decide what 0 means. Some direction, okay? So we want to be able to type in that 0. And actually let me, okay, good. Eventually, we want to be able to type in like a 0 and have them actually go into that room. So they could walk through the cave, traverse the cave. Make sense? Okay. But now for our intents and purposes right now, we want to kind of see that these rooms are getting created. We want to see the kind of the spill through effect. So what we're going to do is we're going to create another class called stats. And what stats is going to keep track of is the total number of rooms and the total number of treasures. Just so we'll know in the end, kind of, since in class here I'm not going to traverse it for us until I show you the solution next week. But we'll know that this cave got built. Okay? So we're going to have 2 fields. So we're going to have a static int num rooms. We'll start off at 0. And a static int num treasures. We'll start off at 0. Okay? And we made these static, which means they're owned by the class. That make sense? So every single time we want to increase our number of rooms, we can use this class to give us a global access to the number of rooms. So whenever a room is born, right at the beginning of our constructor, we're going to say stats.numRooms++. Whenever a room is born, stats.numRooms++. And we want to do this at the constructor level, not here in the for loop level, because we don't know how many rooms are going to be born as a result of that. It'll be a bunch. So every single time a new room is born, we'll call numRooms++. This is where we figure out whether or not we have a treasure. If this dot has treasure is equal to true, which is redundant, but we could just say this dot has treasure. But if it's true, if we do have a treasure in here, we'll say stats dot num treasures ++. Okay? Now in driver,
Question.
Yep.
Will be like supplying the class.
Yep.
Okay, thank you.
So we'll create our one room. This is the cave entrance, if you will. We'll tell that room to display itself, and then we'll go ahead and show the number of rooms and show the number of treasures. So we'll go ahead and run this, and we just generated a cave that had 1 room and 1 treasure. This one had 2 rooms and 1 treasure. 1 room, 1 treasure, 1 room, 0 treasures. 14 rooms, 3 treasures. 3 and 3, 1 and 1. Oh, 66 rooms, 36 treasures. You see that one?
Nope. You went too fast.
Went too fast. Here, I'll stop it at another go. There we go. 65 rooms, 32 treasures. So kind of cool. But we'll see how this can get out of hand really quick. If I come into a room and instead of making this a 3, I make it a 10. I actually lucked out there. Yeah, there we go. It should be out of memory, I think. Stack Overflow. So ran out of memory. Yeah, even ran out of memory with 3 or 4. I think because of the way the random number generator works, I don't think I've run out with 3 exits. That was 237 rooms. Oh, that's a cave. 1,839 rooms, 922 treasures. Legit. All right, so we want to now encapsulate this inside of a cave object. So I'm going to create a cave. Yep. What? Oh, you said bless you. I thought you said question.
Oh, no.
Private room entrance. Right here. I like calling them the entrance. I'm a fan of that. And we'll have our constructor, public cave. And we'll go ahead and say this dot the entrance is equal to a new room. And then we can even steal these. Steal these couple of things here. We won't display that. Instead, what we're going to do is we'll have a public void display method for our cave. That'll say this dot the entrance dot display. But when we first generate the cave, this line generates it. And then we'll report how many rooms and treasures. Then we'll tell the cave to display itself. Cave C is equal to new cave. So that'll generate it. Then C dot display to show us the actual cave. So number of rooms 1, number of treasures 0, 8 rooms, 3 treasures, 2 rooms, 1 treasure, 21 rooms, 12 treasures, so on and so forth. All right, so questions about how this data structure is working. Now, one thing I want us to take away from this is we started off looking at these data structures, and at first they're somewhat intimidating because of all the pointer crap we have to deal with. But now you're seeing how easily we can create really powerful structures. I mean, we just did something in a handful of lines of code that created 2,000 rooms, right? And for your homework, you're going to be creating something that traverses through this. So you could put yourself in the situation where you're standing in this original room. And it's showing, actually, there's no exits for this one, so that's a dud. Bad cave. Okay, so here's one room. We have 1 exit in this guy. So it's going to ask us, where would you like to go? Or what would you like to do? Something like that. So you type in a 0. And when you hit that, it's going to enter into that room. It'll take that exit, and then it'll show you the next room. And when it shows you the next room, it'll show you the obvious exits for that room and whether or not there's a treasure. Then you take any exit, it'll show you that room, so on and so forth. Kind of make sense? Okay, so you can actually walk through this cave. All right, questions about any of the stuff dealing with our cave? All right, So let's go and look at the homework assignment here. So homework assignment number 3, which I'll unlock in a few minutes, and I'll replace the historical code with the code we just did. It's probably pretty close. So we're going to update our crawler game attached to allow a user to traverse the cave. They should be prompted in each room to pick an exit or quit. Every room they enter that has a treasure, they should earn 1 point. Okay, so if a room has a treasure, they get a point. Once they quit, the total number of treasure collected should be displayed to the screen. You should also display the total number of rooms visited. You do not need to let them start over, and you can not move backwards in the cave. So you don't have to add that functionality. You don't have to let them jump back to the beginning, or if they take the exit to 0, you don't have to let them go back. That make sense? So basically it's a start at the beginning of the cave and hope you pick a right path and let you go for a while. If you don't, you've run out of treasure. So it's kind of like a little game in that, if you guess the right path, you can pick up more treasures. But if you're in a cave with 1,500 rooms and you take exit 0 from room 1 and that's the end of the road, you pick up 1 treasure, you're not going to score very well. Okay? So that's the programming side of the assignment. And here, just so I don't forget. Go ahead and add this content. So that's our new file. And then I'll go ahead and unlock this for you. All right, so that'll be the code we just wrote tonight for the cave, even though I'm sure it's pretty similar to what was there before. Now, your paper. Write a 2 to 3 page paper discussing the concept of a MUD as it relates to multi-user dungeons. These were text-based Dungeons and Dragons games similar to what you are writing in your homework assignment this week. What was the first MUD? What were the different types of MUDs? Do people still play MUDs today? What modern game genre has largely replaced MUDs? Well, I answered it out loud, but you have to fill 2 or 3 pages with it. So I gave you the headline. I gave you the headline.
I had that problem with the last paper because I'm like, really, I can answer all of these questions with like 3 sentences, but.
Well, yeah, but so this allows you to explore. So, for instance, when you start looking at MUDs, you're going to see that there was a whole bunch of spin-offs. There was something called Moos and Mushes. So a bunch of different spin-offs from that. And really it represented, these MUDs were around in the very early days of the internet when people, we're still dealing with text-based stuff, when communities of people were coming together with dial-up modems like under Prodigy and these old bulletin board systems. And this was the first, the first existence of games that people played simultaneously with each other. Where now you think about Xbox and PlayStation, it's, Xbox Live is just par for the course. You jump on your Xbox, you're playing against other people. That didn't exist prior to this stuff. So MUDs were really the kind of the beginning point for all that. So it is interesting to look at. All right, so that is the paper. Questions about that? All right. Questions? Anything else we talked about today? Looks like we're done early. I gave you everything. I almost went too far. I almost gave you too much stuff for your. Almost did your homework assignment for you.
That would have been A-okay.
Well, this homework assignment should actually be pretty easy.
Tell that to my brain cells.
This assignment should not take. I would say that the actual coding time, like for instance, when we come back next week and we write it, since we aren't going to have our display issues, I think we'll probably write the solution in about 20 minutes,
Okay.
15 minutes, something like that. I mean, we're probably only going to add about another 10 lines of code for the whole solution, but it's an important 10 lines of code. All right, questions, comments, concerns, bribes.
I wish I had bribes.
All right, I'll see everybody next Wednesday.